party. Okay, you provide the pizza. Okay, so I'm going to break this lecture into two pieces. So today we're talking about applied optimization, which essentially is word problems. So what I'm going to do, so for the first half of the class, I've solved some of them ahead of time, and I'm going to show you the answer. But for these word problems, you sort of have to see how they're done. Like you have to sort of see how I think them through. So for the second half of the lecture, you're going to just ask me random questions from those sheets, and I'm going to try to solve them in real time, which usually ends in disaster. Right? The number one rule of teaching is to not try and solve things in front of the class in real time. But we'll do it anyways. Let's see. So this is not going to be you trying to stump me. That wouldn't be very good. It'll be us trying to work together to solve these things. But I think there will be some benefit just to see how I work through these problems from scratch. All right, so the topic at hand is applied optimization. Ooh, I got a nice new weighty chalk thing. Oh, it's so good. It's a big pen too. Yeah. All right. So basically, applied optimization is using calculus to find the optimal solution to something. Right? So we're just going to use calculus. So it's just going to be a bunch of examples we're going to do today. Most of these examples I pull from Thomas. In fact, that handout I just gave you is a printout from Thomas. I would put those PDFs online, but I'd probably get in trouble. Like, we're not even supposed to have the PDF copy of Thomas in the first place, right? Let alone me pulling out random pages and posting it. So I printed them out. You can take your pictures of them, but most of you should have the Thomas. And if you don't, search the name of the... this is all on YouTube. You may be able to do some effective Google searching to find a Thomas copy. That's as much as I could say about that. Okay, so we want to make a box. So suppose, and I'm not going to write down the problem statements. You have them. So we want to make a box, and we want to make a box out of this piece of cardboard. And the cardboard itself is 12 meters by 12 meters long. And we are going to make the box by cutting out the corner here on each of the sides. Right, so we're just going to cut out an x by x square from each corner. And the question is, so do you see how we would construct this box? If you cut out these corners, you're going to be left with a sort of pattern that looks like this, mostly. And then if we fold this, we can fold it into a box that sort of looks like this, where, what is this side now? Yes, sir. Yeah, this is going to be 12 minus 2x down here. This is going to be 12 minus 2x here. And the height is going to be x. So there's our box. And the question at hand is, it's going to be less organized than usual. What is the maximum volume we can obtain? Right, so this is a very sensible question that would easily arise in the real world, so to speak. Right? How much can we put in a box if we're going to make it out of a sheet of paper that big? So where should we start, you think? Well, we want to maximize the volume. Right? So this means we're going to have some type of volume function, and then we're going to have to search for where it's largest. We have some tools for doing that search. So how can we get the volume of this guy? Well, the volume is just length times width times height. So that's going to be x times 12 minus 2x times 12 minus 2x. And then we want to maximize v. Okay, so we see now that we have this function, what's the domain of v? Right? Because we're going to have to check endpoints, and in order to check endpoints, we need to know what the natural domain of this problem is. Right? So basically what I'm asking is, what are the acceptable values of x? Right? So like if the box itself is only 12 meters by 12 meters, I can't cut out a 50 by 50 square. Right? So what actually is the largest x can be? And it may be careful. How big could I make this x?
12.
No. 12 is too much. 12 is the whole thing. Yeah. 6. Right? You can go right to the middle. In which case you've cut out this square and this square and this square and this square. I was trying to trick you. Right? So x can be, has to be bigger than 0 and less than 6. Okay? So these are going to be our endpoints of the problem. Right? We're gonna want to draw, or at least understand, how v looks like between 0 and 6, and then see where it obtains its largest value. So what is v? So let's do the endpoints. What is v at 0? 0. What is v at 6? Also 0. Okay, so clearly on this volume, we're 0 at 0 and 6 at 6. Or 0 at 6. Okay, so clearly 0 isn't the maximum volume. That's clearly wrong, right? So the endpoints don't give the maximum volume. We're going to have to search a little bit more. So what should I look for now in order to find the biggest value of v? What have we learned over the past few days? Yeah. No. Yeah.
Critical points.
Well, what's the critical point going to give us?
It's going to give us either a max or a min.
Localized max or local min. Okay, so that's important though, right? Because we're going to be able to find the local max and mins, but then we're also going to have to figure out if those localized maximum and minimums are the global maximums and minimums. All right, so let's just get the derivative here. What's that going to be? So I think it's going to be smarter in this case just to combine all of this. So what do we get after we combine it? You get x times 12 times 12. That's 144x. But we should, so you get 144x. And then you get, so this is just 12 minus 2x squared. So the middle term is minus 24x. So you get minus 24x squared. And then you get 4x squared x cubed plus 4x cubed. Oh, no. 24. Did I do this right? Double the product of the middle. Yes, so that's 48. Not enough. 48. Okay, so this means the derivative is what? 144 minus 96 x plus 12x squared. Let's see if we can factor this at all. Well, I can certainly take out, can we factor this at all? Does 96 and 12 do anything? Yeah, I think if I take out a 12, that the remainder is going to be, let me think, x minus 6, x minus 2. All right, so given that the derivative is this, what are the critical points then?
6.
Okay, yeah. Well, critical points occur at x equals 6 and x equals 2. The point itself has to be two things. So this means we have critical points, and let's do the first one. So if we put in 6, what do we get? Well, 0 again. And then if we put in 2, we get, and right, remember, we're putting that into here, the volume. So if we put in 2, so what's 12 minus 4? That's 8. If we square that, that's 64, and multiply it by 2, that should be 128. Let's just check, that's what I got. Yep. Okay, so let's think about what we found then. So we know that somewhere here in 2, we have the point 2 and 128. We know v itself is continuous. It's a polynomial. We know that its endpoints are here and here, and we have to go through this. And we know that this is the only critical point. So actually, this is enough information to conclude that this is the global maximum. Does that make sense? If we had any point that was higher than this, we would have to find a critical point to get back down to it. Another way of doing it is you could take the second derivative of this and prove that the curvature of this at this point is downward. We'll do that for one of the other problems. Okay, so the mechanics in these questions won't be hard, right? It's normally the hardest part of the problem is codifying it as a statement of mathematics. But that process is called science. Right? And I'm supposed most of you want to be scientists, so you're going to have to get good at this sort of codification. Okay, next one.
So,
Yeah.
So the maximum volume would be at x equals 2.
Yeah, but you wanna answer the maximum volume is 128.
Okay.
Right? I'm not looking for a point. Right? So make sure to answer the question when you're done. Right? That should always be your final step. To ask yourself, did I actually answer the question? Well, I guess I didn't. So I should just say this implies the max volume is 128. Yeah, I should help you develop good habits. Now put a box around it. That's what I usually do when I'm writing my test. It's not a bad idea to put a box around your answer. Okay, here's another one, and maybe I'll give you guys a second to try to set it up. Design a 1 liter can that's closed with the least amount of material. Right, so I'll draw that for you. So we have a can like this. Okay, let's call this the height of the can. Let's call this the radius. You want the volume of this can to be 1. What's the minimum amount of material that you need to build it? So give that some thought. Right? Just try to model the question first. Make 1 lap.
So you could find the surface area of the rectangle first and then the 2 circles. For the rectangle. Yeah, so surface area.
So you got to take this. So there's going to be some provided information in this, and you want as much of that as possible.
Yeah.
So to tell you that the volume is 1, that's like really the only thing that's going to be. So you're for sure going to need to use that. And then I'm saying I want the surface area minimized for the, saying I want the material minimized. The surface area is going to be given to you in 2 variables. So that cylinder is expressed by R and H. I didn't teach you how to take derivatives of things with 2 unknowns. We only know how to optimize things on 1 variable, not 2. So I imagine that the fact that you're going to get the volume constraint is going to help you eliminate one of the variables.
Yeah, okay.
But what pieces constitute the surface area?
Times 2.
Well, you can explain it like a kid would explain it, right?
Are you guys doing surface area? No,
You
it's
have to
just.
make this up on paper, you need what?
What's
We were looking at.
so radius is pi r squared.
Circles.
We have two bases.
And you need 2 discs, and then a sheet of paper. What are the dimensions of the sheet of paper? So imagine cutting this can, unrolling it.
Or 2
The
pi.
height.
Yeah, we do. E equals
Okay,
2r.
so don't write D.
Then how about
Yeah, or 2 pi
Yeah,
r.
just do 2 pi r.
I mean, I know this.
roll it?
Okay, so not everyone else knows that.
My notes, to be fair.
Oh, true, okay, that's true.
Circle, which is 2 pi.
And then what?
And then, I don't know, that's why I've been waiting for you guys. Like,
Oh,
no, I mean, I have no idea what it is.
Okay,
What do
okay.
you do? Do you relate surface area to height? How do you do that?
By 2 pi r.
So wait, isn't it this times this?
1 equals pi r squared. This times that. I'm genuinely confused.
I'm just basing it on previous. So
We have the volume,
Yeah, we do this times this.
but we never did surface area.
Yeah, well,
That's one of the constraints. But then you need three things that you need to minimize. Any ideas? That's correct.
a cylinder's volume is pi r squared times h, and its surface area is 2 pi r h plus 2 pi r.
Can't has to be one.
So we've already got
But if you know the volume,
I'm actually gonna watch this.
Are you serious?
I'm literally gonna watch it. I feel like this advice is
anything?
Huh?
Huh?
Like the See, we don't have any problems.
Could we express one variable as
We know
another?
the volume is the
If we rearrange it like that?
You're gonna have to use it. Although it's not like, sometimes they may give you extra information for legal relevance, right? Just to sort of know what you want. There's no information. You need to come up with an equation which you can then optimize, which means like find the lowest or next. You need to find, I think I want to you're going to need an expression that is certain.
I don't know why I'm doing this.
That expression has to be a
Yeah.
single variable.
I mean, like, what am I gonna get out of this?
You're going to have to understand that the volume gives you a constraint, eliminating which
Yeah.
variables depend on the volume. But if you try to understand these things, you get this equation, and that's not, you have to think higher. You have to collect all of the constraints, and then you have to write down the thing that you want. And then you have to hope that the thing that you want is going to ultimately be in a single variable. And then you can undertake the process of optimization. I can show you how to do it with multiple variables, but that's vector calculus. Yeah. Okay, so we have two things here. So what's the volume of this can given by? What's the volume of this of a circular right cylinder?
Isn't it pi r squared h?
Yeah, pi r squared h. Pi r squared h, and we know that this is what in this for this problem?
Equals 1.
Yeah, this is 1. All right, so this is something that we call a constraint. Okay? So what's the thing that we're trying to optimize now in this situation? Surface area, right? We need the least material. Material basically means surface area in this instance. So the surface area is going to be 2 circles of radius r plus a sheet with what dimensions, right? So you have to imagine you take this cylinder, and just imagine I like make a cut and I unroll it. So if I unroll it, the height's going to remain the height. But what's this side? Yes, sir.
What is the circumference of the circle?
Yeah, it's the circumference of the circle. If you imagine that I have to pull this and like connect these two sides, this is going to have to be the outside of the circle. So you got 2 pi r down here, which means the surface area is given by 2 pi r squared plus h2 pi r. Okay, so now it's our task to minimize the surface area. But what problem do we have? Do you know how to minimize this? What's preventing you from minimizing it? It's two variables. We haven't even talked about what functions of two variables look like. They're surfaces. But let's not worry about that. Yeah?
Could we rearrange the first equation?
Exactly, right? So if you're not using your constraint, you're doing the problem wrong. Right? Because obviously the amount of material you'll need is going to be totally dependent on the desired volume. Right? So usually what these constraints let you do is eliminate one of the variables from the function that you want to optimize. Okay? Like at least at your level, you're more or less assured that you're going to be given enough constraints to do this. So let's just rearrange this a bit. This means that, what did I do it in the notes? Did I arrange for H or R? I arranged for...
Doesn't matter.
It doesn't matter. I just want to make sure I'm consistent. Well, actually, I think I did something a little bit smarter here. So when we're doing substitutions, I want to replace the most amount of stuff with the most amount of other stuff. Right? So we're going to have to start practicing this because when we start doing integration by substitution, you're going to need this ability. So I want to match as much of this volume equation with as much as this as I can. So what do I see? I see I have, this is 2 pi r, right? Oh, I'm missing an h. Oh, no, this is, yeah, let me this is 2 pi r h, yes? And this is pi r squared h. So this means that I have, let me see. I basically want to replace h pi r with something. So h pi r is equal to, h pi r is equal to 1 over r. You see that? I just divided by r, right? Divide by r, you get pi rh is equal to 1 over h. So that means I can replace this pi rh with a 1 over r. So here you get 2 pi r squared plus pi hr, so that's 2 over r. So just a little trick to like help you simplify faster. You could have solved this all for h and put it in, but then you would have had to do a lot of simplification in the interim. Right, so if when doing these substitutions, especially substituting in constraints, try to match as much of the constraint equation as you can to get this type of nicer simplification. It'll save you a ton of time. Okay, so we have the surface area now is equal to this. So let me just write it, the surface area with respect to r. Okay, so now we can minimize surface area with respect to r. So how do we do that? Well, let's take a look at this. Is this a nice function? It seems to be everywhere. Oh no, that's not true. Okay, so we need to find the domain. So what is r? Like what is the constraints we have on r here? Well, certainly r has to be bigger than 0. And what's the maximum r can be under this constraint? 1, I suppose. If I make the radius 1, then basically the surface area is 1. If you imagine making this out of actual material, right, the bigger I make r, the shorter the can has to be. And the maximum I can stretch this r is to, well, I can't actually get to 1, right, because that would make the can dimensionless in height. So that's why I put that boundary there. Okay, in any case, let's check the endpoints for those r's. So the surface area at 0, so these are endpoints. We have the surface area at 0 is, undefined. Actually, it's not really undefined. It's positive infinity if we come from the right. So more accurately, it's positive infinity. What's the surface area at 1? So the surface area at 1 is going to be 2 pi plus 2. So we're just going to have to keep that in mind. I don't remember getting that boundary point yesterday. Okay. So what should we do now? Where's the maximum value in here? Well, we're going to have to use calculus, right? So we have this surface area equation, this one. And this is the thing that we're going to want to minimize. So let's just go ahead and take the derivative of the surface area. That's going to give us what? 4 pi r minus 2 over r squared. So what points do we get out of that for critical points? Now if we want this to be equal to 0, that means that we have 2 over r squared is equal to 4 pi r, which means that r cubed is equal to 1 over 2 pi, which means r is the third root of 1 over 2 pi. Okay, so now we just have to check that the critical point gives us a smaller value than the boundary did. So the boundary gave us this. That will actually be a problem, so I'm hoping that the boundary is not going to be the answer. Okay, so what happens? So this is critical. So let me just, I don't know, go up here. So this means we have a critical point 1 over 2 pi to the third. And then I put that in the volume equation, which gives me pi, that's squared. So pi 1 over 2 pi to the 2/3 times, I'll use the wrong equation.
Yeah.
Which one was confusing? Well, tell me what you're confused by.
The whole thing.
A
Got to stop me then earlier, right?
Like this one example, like the other one was straightforward, actually. But this one in particular, I'm like, feel.
Okay, well, let's walk back then, okay? This is the volume of the cylinder.
Yeah.
And then the thing that they're asking us to do is to create a cylinder of that volume with the least amount of surface area.
Right, and so we know that, so we're given our constraint. So in the question, 1 liter.
Yeah, so we're told that. We're told the volume, we want a container that can hold 1 liter of substance. And they say make that container out of the least amount of material that you can.
Okay.
So this is the volume. So that's a constraint. That's something we're told. Right? The surface area is something that we had to build. Right? We had to be clever enough to say, oh, material is surface area. And surface area in this question will be equal to this. And then we used our volume to eliminate one of the variables. I could have eliminated r for h. But the reason I'm doing that is because you don't know how to do optimization on anything else besides functions of a single variable.
Okay.
Right? So we're obligated to do this. Like, that's not to say that I can't look at this shape. It's just a surface.
Right.
And then we have to start talking about where we can find pools. Right? You can do it on this. It's just, in this case, you have a constraint which makes it easier. And for you, at your level, we're always can make it so that you have a constraint that gets you to a single variable. So once you get the single variable, then you can go ahead and ask, like, so this is the thing I want to make minimum.
So were we isolating? That's what we're doing, right?
Well, no, like this is the equation for surface area. I'm not solving anything. I'm saying what is the minimum value of this function.
Okay.
Like if I say radius is 1/2, this will report to you what the amount of material you need.
Oh, okay.
And I want the minimum amount of material, but anything satisfying this equation will give you a can of 1 liter. Right? We have many options for a can that can hold 1 liter. This is going to tell you the optimum R to pick. That's the point of these questions. That's what applied optimization is. Well, first Suki and then you, yeah.
Oh, never mind.
Okay, cancel Suki, yeah.
So I understood when you took the derivative, I just was wondering what you did after that.
Well, remember I've taught you other stuff before this. And the other stuff I taught you before this was how to find localized maximum and minimums on curves. Right, we could draw this. I don't know how it looks like, but it's a parabola which somehow decreases over time. I don't know. It's something like this. Right, so if I told you that this is what the surface area is with like respect to R, like we're really looking for that. The minimum amount of surface area to use. Right, and given that we're not plotting these things, or you don't have plotting software on your midterms, you have to use algebra in order to deduce what the minimum term is. And the minimum term are always going to happen at these absolute maximums or minimums, where the critical point, well, where the slope is 0 or undefined. So all I'm doing here is like everything that we've been doing before, just like characterizing this function, right? So I'm just trying to find critical points, right? I'm just searching for this point. If you were to plot this, you can plot this. You can see that it should have some minimum, and I'm just searching for it. But the whole problem's, like there's not really much calculus in here. The calculus is stuff that you've already done. The stuff that I'm trying to teach you is actually deducing an equation that's going to be amenable to calculus. Right? That is entirely the difficulty here. The calculus is like incidental. Right? So it's like get to here, and then basically all I should write is then use calculus to minimize the curve. Right? So I'm just minimizing the curve down here. So this was a critical point that I found. It's the only critical point. Right? Therefore, it has to be the minimum. Well, we have to do some other work for that, but I can show that we have upward curvature here. Right, so basically, I'm just using calculus to find the minimum point. Right, that's all that's happening here. Right? So when you hear about data science and artificial intelligence, it's basically just doing this, writing they'll have a very complicated equation like this in like 100 variables and trying to find the minimum. Yeah.
Right where you take the derivative, right? You isolate it, like you brought form.
Because I need to know when the surface area's derivative is 0. I'm just finding critical points. This is something that we've done like 100 times, right? But I'm isolating for a very specific purpose, right? I'm saying, look, this is the R where you're going to have flat tangent. Should we step back and talk about like what we learned about geometry?
No.
Okay, let me just remind though that like we spent a lot of time trying to like classify stuff like this, right? And we weren't doing it for shits and giggles. We're doing it because like most problems of science are ones of we either need to know how big the curve can get or how small the curve can get, right? This is knowing like optimization of the optimal property will either be at here or here, depending how we define the optimal property. We went through a lot of discussion basically to determine that these type of local max and min points occur concurrently with this special geometry. Like you're always going to get a minimum point, and that will have to produce a flat tangent. Right? So again, like really I could summarize everything we're doing today as get an equation in one variable and then use calculus to find where it's smallest or biggest. Right? And like we just have to remember that when I close the interval, you are guaranteed to find a maximum or a minimum globally. We have a theorem that says that.
But the issue is getting that equation.
Yeah, that's called science.
Yeah.
Right? So this is something you have to be good at. Right? It's just taking a problem from the real world, quote unquote, and codifying it. Right? And I'm just to prove to you that calculus is useful. Right? This is basically why we teach you calculus. Right? Optimization is like probably the best example of a real world application. Okay. Any other questions? Okay, that's fine. I like this, like, because this is an important topic.
Like, I have a question.
Yes.
Can you like go back? When you put 2 over r squared equals 4 pi r, why did you divide by 2 pi? Like, why is 2 pi in the denominator in the next line?
Well, because I just isolated for r, so this r has to come up and this has to go down.
Didn't you just like divide by 2 though?
Well, there's a 2 here.
Yeah.
So if I divide by 4, that's a half. Right? And then if I divide by pi, that's 1 over 2 pi. This? Right?
Yeah, can you just write like one more line in between that and the one on the right? Like, because there's like a step.
Sure.
Okay.
2 over 4 pi is equal to r cubed.
Oh,
Is it enough?
okay.
Okay. Okay. Let's move on from this one. Let's try another one. I think you just need a bunch of practice.
So, Professor, what's the answer to this?
Well, that's the answer.
That point?
Yeah, like this will give us the maximum, or the minimum surface area required.
So you plugged in r equals into that equation, but if you don't have a calculator, how do I?
This is a number. This is a number, right? So you don't have to calculate it, right?
What is it representing, though, that number?
The minimum surface area.
But is it?
No, you plug it into the SA r
And that's the y.
Okay, it seems that we like don't understand like what we have done like through the last 2 weeks. Because I'm just trying to like bring this into science now, right? So like if I phrase this problem of where is the minimum and maximum on this, you guys would be able to do that.
Okay, wait.
Yeah.
So if to answer this question, you're saying design a 1 liter can, are we then providing the radius and the height of that can to make it?
No, answer the question. What is the minimum amount of surface area required to make a can of 1 liter?
Okay. And then
So you provide the material,
so
the
you
amount
would-
of material.
You would plug in this value, the x value, and this is the surface area?
Okay, let's try another one, right? Because maybe it's like this problem itself is just tripping us up, right? So we'll do another one, and then maybe we'll do 7 more, and then.
I think it's the,
Okay, no, critical point.
sorry, he was asking about the y point.
There was no trig in this question.
Sorry, the pi, like plugging the coordinate that we got.
Okay, do you want to start this problem from scratch then?
What do we plug
Let's
in to get the surface?
move on. Okay, we have to move on, right? Okay, let's try another one. This, you just need some practice, but like again, like you have to understand everything we do. Right? It's not going to be the case like these aren't isolated classes. These classes are dependent on the stuff that comes before. Okay, look, let's try this one. Here is a parabola. And this parabola is 12 minus x squared. And I'm going to inscribe a square in it, like this. Here's the square. Let's call this rectangle R. So does everyone get the setup? I have a parabola. That parabola is 12 minus x squared. I'm putting a rectangle. I'm like positioning it on the x-axis. And I'm going to state this very simply then, right? Maximize area of R. Okay, so I'm going to write down the steps, right? You need an equation of a single variable, and let's call it AX, right? Equal to the area of R, okay? So let's think about this. You're going to get an equation of one variable saying, maybe, I don't know, like this is the area of that rectangle. You then have to search for the highest point. You're trying to maximize the area. So that's why I say sort of half facetiously, but half seriously, like use calculus, right, to solve or to optimize. Which basically just means use all the algebraic and geometric tools at your disposal to figure out where the area is biggest, is another way of putting it. Right? So calculus is just a way to figure out how to answer these questions when you're like don't have access to a graph. Because usually these in science these functions will be a lot more sophisticated. But give this one a go, right?
Sure, the critical point is minimum, I understand that. I totally understand, but you plug this into the surface area equation, which is here, to find the surface area, right? Then how do we find the surface area?
You were looking at the R here. This is where you're looking at the minimum. This is where
Oh, we figured out that the radius that would give us.
Okay, and then you get this, which is the derivative of the surface area, which is just the slope.
So this is your point on that minimum.
That's not actually the question.
So it's a minimum, right? This price is that
Okay. So how do we answer the question with this?
minimum amount of
So how,
This is line
so what's the answer?
this.
So that's the minimum amount of material.
Like this.
Wow, okay. So you're fucking number.
Yeah, but it's still gonna be a number, but the thing is, I wouldn't know how to calculate it, like, how do I find this?
I guess you just leave it unsimplified.
The minimum point is
Yeah, but then I wanna be, yeah, I don't know how to read.
I mean, your wife would be the unsimplified stuff.
Yeah, I guess so.
Because there's no variables in here, there's just a number. Yeah, I guess. I mean, it's a number, it's not, it doesn't have a variable.
Okay, it's 2x, so we could work at one.
They're both the same.
The same, just, it's kind of like.
Yeah.
What's this one? That one. I told you at X value X.
That's the, like, that's a parabola. So what is this?
So what's the distance from that, from the origin to the basketball?
So it's giving me these, so I can find these points. From here to here. Because this is on the parabola, right? This point's on the parabola and
Yeah,
then.
but you don't know what the point is. Oh, I mean, okay, yeah, let's do that thing. Okay, let's use that function.
This
What
point
is 12 minus x squared? Let's do that.
isn't that distance X? Thereby, the rectangle has area. That's how you have to think, right? It's like, don't just like go right to the concept. Let's start with a simple problem. I need the area of this rectangle. What is the area? And then you can start thinking about it.
Because if you think about it, we plug in x is 0, so
At
then
x
at
is
0,
You know what I mean?
So at least we have one, yeah, 1 point.
we have 0 to 12.
Don't try to just follow a set of instructions. Try to understand what you're doing.
If it's a rectangle, that means the other side is also
Think about the way you made it from here. Wait, so my x is 0. Yeah,
So that means that I don't know what this point is. I know what
do
this
you know if that's the maximum point?
Then that would be curious.
That's not good enough. Calculus actually doesn't matter. Spend a lot of time on isolation.
Yeah, so
How is it going to follow this number? Yeah.
which means that's the times. So then if I put that back in, it's just gonna be here, it's gonna be 0. I don't know what it's gonna be here. But it's not.
You know application is purely mathematical.
Not, I don't know the point for the triangle. I mean, the rectangle.
But don't try to codify like a set of instructions. You have to understand
Oh, no.
broader, like model the problem, optimize it. Really.
We're trying to figure this out, like the steps that you try to do. So, we just don't know how to, like, we found this point. When you find the
Well, I'll just talk it through, but like, what's the area of that rectangle as you draw it?
yeah.
What's the length of the rectangle? What's the width?
I know, and that's what I'm trying to find.
But you know it. You're just confused again because there's no number. But like, do you not know what any point on this is? That's x, 12 minus x squared. What do you mean the actual number? Like, you understand there's going to be a rectangle at every point on the parabola. We are trying to find the single one that means it gets the highest area. So if that was a single rectangle, we've done something wrong. Right? The first equation should have some independent variable. That's the thing that you're optimizing against. Okay, should I go through it? Okay, because I'd really like to get to Snell's law. Okay, so I'm hearing a lot of things about that, oh, I don't know how to do this. There are no numbers. Okay, so let's step back and just think about this a little bit more slowly. What is the area of a rectangle given by? Length and width, okay? So we need to figure out the length and the width of this guy. Now, I told you that this curve is 12 minus x squared. Thereby, any point on the graph of this is easy. That's just x. 12 minus x squared, okay? So what is this distance from 0 to here? I heard it. X. And what's this distance? That's 12 minus x squared. Okay, so what's the area of the rectangle? Yes, miss? Yeah, 2 of these times that. Okay, so don't overcomplicate these problems while you're doing them. Right? Don't just do things one by one. The first thing that you had to do in this question was determine the area of the rectangle. Don't forget about everything else. Okay, so we know that the area of R, let's call that A, that's going to be 2 times x times 12 minus x squared. Okay, so now we need to know what the domain of R is. So what's the minimum x I can choose and what's the biggest x I can choose? Can I choose x like here? No. So clearly I can start at 0. That's going to give me that rectangle, really the single line. And the biggest I can move it to is there, which is the square root of 12. Yeah? So I get x can be at least 0 and at most the square root of 12 with open brackets, right? Because you can't actually obtain those points. What do we get at these? So the area at 0 is 0, and the area at root 12 is 0. So clearly those aren't maximum points. All right, but this is good news, right? Because if we were able to actually draw the area of this rectangle, like its graph, between 0 and root 12, we know that it has to pass through these 2 points. Yeah? So that means the critical point that we find is going to necessarily be an absolute maximum. Well, provided it's positive. We may actually find a critical point that's lower than 0. Let's hope not. Okay, so how do we optimize this then? How do we find the turning point of this area? Or we want to find where it does that. Yes, sir? Yeah, so we need to find the critical points of this area function, right? To try and deduce where this is happening. All right, so that means we have the area. Let's just expand this. We're going to get 24 x minus 2x cubed. So that means the derivative of the area is 24 minus 6x squared. The area then is 0, means that we have 6x squared is equal to 24, which means that x squared has to be equal to 4. Okay, so this really means x is either plus 2 or minus 2. But what do we do with this guy? Yes, sir? Yeah, like this is not a solution that is in our stated domain. Like this is going to happen when we're modeling physical problems. Like mathematics has no problem with negative height trees. Right? Like stuff that doesn't make any sense in the physical world is fine in mathematics, right? So sometimes like this is called inadmissible. Right? Because we can't have a negative distance on a rectangle. So we just say, all right, we don't, that one's outside of our domain. Okay, so this means I found a critical point at x equals 2. So like at x equals 2, we know that one of these two things are happening. Right? There's actually there's either a localized minimum or a localized maximum. However, I know that the original area function is continuous. It's a polynomial. It's the nicest thing. So thereby I know it has to go through this point and this point. So the critical point that we find has to correspond to a localized maximum. So we have x equals 2. So how now do I solve this problem? I know that the area is maximized at x equals 2. So how do I answer now? Yeah.
Would you just plug it back in to get the area?
Yeah, I could say maximum area is equal to the area at 2. That would be a fine way of saying it. Or actually putting it in, which gives you 48 minus 16. Is that 32? I guess we should write meters squared. I don't care too much about the units. Is that a little bit better?
Yeah.
This one is a little bit simpler though because there's no constraint. So we have to do another one with a constraint. And again, it's just like related rates. You just have to do as many as you can, which is why I gave you that handout. Each of you should have at least like 30 questions to try. Okay, we'll try another. There's some real neat property of light that I wanted to show you, but let's try this question first, because the one that I'm going to show you with light gets a little bit messy. So, okay, I'm going to give you another one, and you give it a try. So I'm going to give you a circle of radius 2. The radius of this circle is 2. I want you to inscribe a rectangle in here. Let's call it R. And I want you to maximize the area of R. Give that a try. Not much information here. You're going to have to like remember stuff. Like what is the equation of a circle? Which is something that everyone on the final last year sort of did wrong. I think we gave a question very similar to this on the final. And not many people did it because they forgot that they knew the equation of a circle. So it's very similar to the question above it. And so you can try to follow that along.
But the radius equals 2.
Mm-hmm.
Not the size.
No, the radius of the circle is 2, and then you have to inscribe a square inside of it.
Can you use a triangle?
Do it whatever way you want. There's a ton of ways of doing it. Yeah.
I'm sorry.
Oh, I'm talk with Mike. We technically have no policies tracking the quizzes. So I'm going to talk with Mike.
That's not really-
Set it up as a way to do it.
I was thinking of doing it. Look. I can try like this.
Just you send me an email at the end. Yes. That's fine. It's just a quiz, right?
Oh, you
Yeah,
can
read
read
through
the side
the,
with 2 minus.
the
I
book.
I'm trying literally every question.
Oh no, because these problems I did, I put them in the
Like
comments.
these little.
Yeah, I
Give a little bit
realized.
more explanation.
So therefore, the whole side length would be 4 minus 2x. So what would the height be? Also, I'm sorry. Which equation should I use? Like the radius? What's that point? Oh, you mean like that?
X squared plus y squared
Yeah,
equals
yeah,
4.
This would be
The equation of this circle.
like in a plane. On a plane. Like if you put this on a graph. This is the equation.
need to take 2 minus x to get this part and 2. So 4 minus 2x. X to get this length times
All the animals here are
width.
totally
Okay, and then this is just width, and then this is going to
occasionally transfer. They're like deer. You know when you like see a deer? It's like all of it's a deer. It's like not that big of a deal, but it's rare. So yeah, deer, like it's like deer. Now the context of deer, they're like really attractive.
Because this length is just 2 minus the x over here.
And koalas are.
No, I'm saying because this length over here is x, and this whole thing is 2 minus x. Because it's this whole thing minus this part, which equals this one. So, I'm sorry. I meant this whole thing is 2 minus the x equals just this length, right? So it's just, yeah, so it's just 2 minus x. That makes sense, right?
Oh, yeah.
Well, we're trying to find these.
So we have the area, we have the equation of a circle. Now we have to find what?
This is
Maximum area of our, of the rectangle.
wait, and this is our area R.
We're gonna get different. All rectangles it's fine.
We have a good start.
Question I'm asking, which one of these areas? So you don't need an equation for the area.
So,
So what's this domain? So x is equal to
8 pi. You want an equation for the area of the rectangle. That's gonna do things to change. You're basically.
no, 2. One of the points is 2, right? And one of the points is
If I put x there, what the area?
or no, 1 over 2. Yeah, half.
You have to figure out an equation for the area of the rectangle.
it's similar to this question.
So the domain is this, right? Because
So-
I'm taking n back, or like I'm finding x.
You're setting it to 0. Just trying to
Yeah,
figure out.
yeah. I'm setting it to 0. So this is our domain, right?
Or,
You need to deduce the length of it,
Which is x is
you just expand.
or some other thing.
Yeah, I'm gonna let you work a bit more. So I'm gonna give you a hint.
Wait, what?
I'm finding the
Oh,
domain
like
to
this?
check where it's between, right? So x is equal to 2, and then this is equal to 2, right?
So it's 2 minus x times 2 minus x. So it's x.
Well, before I do that, look, you know what, I'm starting the domain for everything to make sure like you're
Yeah.
between that and so like negative 2 equal between that. That's what I was doing.
Was it multiplied to equal to middle?
So
So,
2x equals 1 and then x is equal to 2 anyway, because it's like 4 over 2.
I have a y.
4 over 2.
That's, yeah, but like this is
So
short.
it, what?
Yeah, no, so there's 2 points, there's 2 critical points, or it's a double critical point.
The width isn't 2.
And then now we take the derivative,
That's x to 0.
expand it.
No, but what's the domain? We don't know the domain.
So wait, is this 2?
Oh.
A domain is 0.
Yeah, it should be an x.
We don't have that.
Okay, here's a little hint that could help you write down an equation if you like, because this rectangle is actually 4 triangles. So if you got an area of one of the triangles, right, that can simplify things a bit.
No, but this is just 2. But this is
That would
2.
simplify it much more.
Okay, good. At least you cross things out and start over again.
Screw that shit, that was so stupid.
Hey, Professor.
Yes.
We're stuck.
Kiss that.
So we've gone up to the point. And now we're at.
The rectangle of maximum area has 0 area?
Yeah.
Well, you should at least be confident enough to know that that can't be the answer.
But-
I would give you marks in an exam if you wrote that and said, this can't be the answer. Honestly, it's better than saying that like you believe that this ridiculous like value is the answer.
your goal is to always communicate to the TA that you know what you're doing. And saying, I have to reject, I know something has to have happened. I must have miscalculated something because this cannot be the solution. Don't forget, when you're optimizing, we're finding both minimum and maximum points. Right? So the process is, you're not necessarily only finding the highest points. You're also finding the lowest. Maybe I'll get one of you to do your write your solution on the board. Okay, I'll give you maybe another few minutes. And maybe I need that board on top.
How can I make legible?
Okay, so let's work this out together then. So we know that this value here is what? So this is going to be the point on the curve. Let's just call it x0, right? That's that point. That means this length here is what? Well, it's 2, right? That's the radius of the triangle. So that means the area of R is equal to 4 times the area of the triangles. So area of this triangle. So the base is going to be x. Its hypotenuse is going to be 2, which means that its other side is going to be 2 squared minus x squared. Everyone with me? Please stop me before I get to the end. Okay, so you agree that the area of this rectangle is comprised by these 4 areas of these triangles. So what's the area of this triangle then?
Where'd you get the height of the triangle?
Well, I have the adjacent, I have the hypotenuse, so I just use Pythagoras to get the remainder. Right? This squared plus this squared is this squared. So what's the area of a triangle? 1/2 base times the height, right? It's half of a rectangle. Okay, so we have 1/2 the base times the height. Okay, so this actually works out to 2x 4 minus x squared. What are the boundary points of the area? Or what is the maximum and the minimum x that we can choose? Well, can I choose x out here? Why? What am I beyond? The circle. Okay, so but what's that point here then? 2. So what's x constrained by? And what's it constrained by on the other end? 0, right? It's the same rectangle if I go here. Okay? So we know that here our x has to be constrained to 0 and 2. Right, so let's check our endpoints. Area at 0, well, that's 0. And area at 2, well, that's 0 again. That shouldn't be any surprise, because that's the rectangle we get if we bring this point down to here at 0. And if we bring that thing up to here, it's just an up and down line. That's sort of a good problem to have. Okay, so we know that if we were to plot the area, that the area goes through 0, 0, and 0, 2. Okay, so this is the area with respect to one variable, x. Let's just take the derivative of it. So we have a prime is going to be derivative of the first, that's 2 times the second, 4 minus x squared, plus the derivative of the second times the first. So you're going to get, that's over 2 4 minus x squared. Okay, so now we need to know when this is equal to 0, right, to obtain the critical points. So let's say that this is equal to 0. That means that, okay, so first of all, these 2's are going to cancel. Why do I have a negative in here? Did I miss a negative? No, I don't think so. Oh, I missed the negative. I missed a bunch of stuff. Oh my God. Where's my mistake? What did I miss? Okay, let's try again. I'm taking the derivative of this guy, right? 2x times 4 minus x squared. I forgot about chain rule. So let's try again. So it's the, well, I'll write it. Okay, so I need to do this, right? The derivative of the first times the second plus the first times the derivative of the second. So let's try this again. So this is going to be 2 times 4 minus x squared. And then you're going to get 2x, and the derivative of this, that's a half 4 minus x squared. But I totally forgot about chain rule, right? I have to multiply by the derivative of this, which is minus 2x. Okay, so that means, what do we get? I can cancel out those 2's over here, so I'm going to have a 2. 4 minus x squared minus x squared over 4 minus x squared. Whoops. So let's keep going. So if I continue from there, I get x squared over 4 minus x squared is equal to 2 times 4 minus x squared. Everyone agree? I just moved one of the terms to the other side. Yeah. Okay, so if I multiply through by this, I'm going to get x squared is equal to 2 4 minus x squared, which means that I need x so that, so this 2 multiplies by that x. It comes here. I get a 3x squared. That's equal to 8. So that means I need x squared is equal to 8/3, which is not something that I remember getting last night, so let me check. Did I make an arithmetic? Did anyone see if I made an arithmetic error?
Minus 2 is squared. On the other side?
Here?
Yeah.
What did I do wrong? I'm missing a 2, aren't I? From there, yeah?
Yeah.
Yeah. Okay. Yeah, that should be a 2. Yeah, because I forgot about that one. So how do I carry that? Let me see. See, this is why I should just start over, but okay. So with that 2, that should get rid of this one, which gets rid of this, which gets rid of, that makes that a 2. Right, which makes this a 4, which means we get x is equal to plus minus 2. We reject the minus 2 solution because it's outside of our domain. Let's try something else this time, right? So we have the area prime is equal to this. So the second derivative is what? We're going to get, screw that. We could do it the other way. Like basically at some point you're going to have to argue that the critical point that you found is the one corresponding to the absolute maximum. It's like in this case I know that like we have 2 points that are sitting on the origin, that the function itself is continuous. So in order to go from here to here, it has to pass through the critical point. So in this case, since the critical point is positive, we have a situation where the function has to go like that. So it has to be the absolute maximum. But just note, when you're doing this, you have to give some type of argument to specify that the thing you found is like a maximum or a minimum, right? Either by like looking at the curvature of the function, by like checking the second derivative, or by drawing this number line and investigating the increasing, decreasing behavior, right? Okay, so let's just finish this. So I need the maximum area occurs at x equals 2. So that means the maximum area is a of 2, which is 4 times a half times 4 times a half is 2, times 2 is 4, times 0. What?
Just the beginning. I mean, I gotta understand where he's coming from.
Oh no, I did it wrong again.
Okay, so can you just tell me what the 4x?
Oh, guys, not a good day.
Like the 4x, where is the area of R is the rectangle, right? The x is.
Anyways, I screwed up the arithmetic, but it's correct in here. So like, go by my notes today. Not the best lecture. Okay, so I just want to show you Snell's law, and then we'll try to do some more questions like independently. This is why I recommend that if you make a mistake, you have to start over again. And I just didn't want to start over again in front of an audience of like 100 people, but yeah, that's what I should have done. But like, that's the moral of the story basically, right? You have to get, like they're asking you to find the maximum or minimum value of some property. You need to get that as a function of one variable and then use calculus. And so we're going to do one last thing today, which may go disastrously. So, but let's try it anyways, because it's a very interesting property of light that we're going to work at.
That's the height? The height is that? Or, I mean, well, yes, the other part. Okay. Okay, so you got the 4x, and I got the triangle, I can understand that. Where's the 1/2 then? It's 4 times 1 over 2 times x times.
Okay, physics.
Is this no longer the area of the rectangle?
So I'm just going to tell you something interesting about physics. You don't actually have to know this. It's just kind of fascinating, and it's an application of what we're doing today. So you know light? Light, right? So they draw this in physics like this, as light. And so you know when you look into a pool, if you like stick a ruler into the pool and you look at it, it looks like it's bent. So this is called refraction, right? So when light passes through a medium, if it goes from like one medium to another, like air to water, the light actually, okay, so let me do this here. So like this is the surface of a swimming pool, right? This is water. So it turns out if you shoot a beam of light from this point A, it's going to hit this water. There's going to be a change in a medium. So like this is maybe air. And down here, this is water. So what's going to happen to this light is that it's going to sort of bend once it hits the new medium and goes to B. So I'm going to draw some values in here. This is theta 1. That's going to be theta 2. Now, the amazing thing about light and nature generally is that it seems to solve calculus problems naturally. Because light will somehow, so if you shoot this light, it's going to figure out this angle so that its travel time from A to B is minimal. It just does that naturally, right? So light will choose that angle so that travel time from A to B is minimum. Find the relationship between theta 1 and theta 2. Okay, so let's write the question over here, right? So travel time from A to B is minimum, okay? Find how theta 1 and theta 2 are related. Okay, so we need a few things, right? So we have a lot of freedom to solve this problem. So let's start labeling stuff. Let's say that C1 is the speed of light in this medium. And let's say C2 is the speed of light through this medium, like in the water medium. Okay, how do you get, is there anyone taking physics here? Yes.
No, I'm not, but I have a question. The theta 1 and theta 2, where's the theta 1? Is it just the midline or is it all the way around?
It's this
The
angle.
whole thing, okay. Oh, no.
Yeah, not the whole thing. This, right?
Okay.
Which also ends up being that one, I guess.
Okay, thank you.
Where was I? Okay, yeah, so we need to somehow get travel time. So what's the equation that's like relating speed, distance, and time?
Velocity. Velocity equals distance over time.
Yeah. So your velocity, or speed, or c, is equal to distance over time, which means that time spent is equal to distance over velocity. Right? Okay, so what equation do we need to write? What will we need to optimize in this case? It's in the question. Yeah.
Are we like optimizing the angles?
The time.
Travel time from A to B is minimum. Right? So they're telling us that the travel time is minimum. Right? So we should write an equation for the travel time. Yeah. So what is the travel time in this case? Well, we need to know distance and velocity. So we need this distance, and then we need this distance. Okay, so we got to label a bit more. So let's call this position here, so I can be consistent with my notes. And in my notes, you'll see that the picture that I drew is half the size of the page. So I practice what I preach. So let's call this distance here A. Let's call this distance here B. And let's just call this distance here D. And we'll call this guy X. Right? Because we get to come up with labels. So X will be chosen so that this will be a minimum travel time. This is D minus X down there. Okay, so maybe I'll draw a brand new. So we're going to leave this here. And I'm going to draw a new picture. Because basically what we need is we need to know what the distance is here and then what the distance is here. So what is the length of this line? All right, the one that goes from A and then hits the axis.
From the origin?
Well, how I drew it, right? So this is going to be A. This will be X. So thereby this is going to have to be A squared plus X squared. This one has height B and then adjacent D minus X. So this guy here is going to be B squared plus D minus X squared. Square root. Do you agree that these are the distances on those lines? I'm just using Pythagoras to pull those. That's not physics or anything. Okay, so, but now I know that the time, so travel time, let's call that t. So it's going to be equal to this distance divided by velocity. So it's this distance divided by the velocity, or the speed, plus the next distance divided by the velocity through the second medium. All with me? How many unknowns do we have in this equation? You need to start seeing the difference between letters, right, that are fixed and a letter that is an independent variable.
4 unknowns.
No, one. This. Right? Just because something's a letter doesn't make it unknown. I specified that C2 is the speed of light in the medium. Right? That will be fixed by someone. Right? We have an equation for a circle, pi r squared. Right? You give me r and I'll give you back a property. But because the angles are going to be fixed by nature. Right? If I shine a light into the medium, you can measure that and get it back. Right? So this x is the thing that's going to move, right? That's going to be optimized. So anyways, you have to treat these a's, c's, b's, and d's as like fixed numbers. Right? X is the thing that's allowed to move. Okay, so we need to now minimize t. Right? Because this is the travel time. So if I move this x, right, we're going to have a different travel time depending where I put that. And for one of them, that will give you the minimum travel time. And that's the one nature is going to pick. Right? So we're going to minimize this. So let's take the derivative here. So this means that t prime, and let's see if I can do this properly. So I'm going to take the derivative of this. That's going to give me 1 over 2 c1 over 1 over a squared plus x squared multiplied by chain rule. So there's a 2x plus 1 over 2c2. That's going to be over b squared plus d minus x squared multiplied by chain rule. So in that case, we're going to have multiplied by 2 d minus x multiplied by minus 1. So take a look at this, because it's a chain rule. They got to keep chaining till the very end. I already screwed this up once in the lecture, right? So got to be more careful than me. Yes, sir.
Shouldn't it be 2x plus 2h?
2x plus 2h. Sorry, for which, this term?
For the chain rule. Shouldn't it be 2x plus 2a?
2. What's the derivative of a squared? It's a number, right? Which is why I was going through all the motions, right? Because now those are fixed constants that will disappear. Okay, so we need to know when this is 0. So when is this 0? Oh, this is going to scare some of you. Okay. Shouldn't be scary. I'll walk you through it. We'll get through there together. Okay, so we want this to be, oh, I think I actually simplified a bit more. Okay, so let's simplify a bit more. So this 2 will cancel with this 2. So what am I going to get on here? I'm going to get x over c1 a squared plus x squared. And then this guy, that 2 is going to cancel with this 2. I'm going to have a minus. And then on the top, I'm going to get a d minus x. On the bottom, I'm going to get a c2 b squared plus dx squared. Can we make any simplifications here? This is beautiful. This is why this gets a name in physics. It's going to be a law of nature. Okay, so let me just call this guy h2. And let me call this one h1, right? The first hypotenuse, the second hypotenuse. How can I rewrite this? This is actually x over c1 h1 minus d minus x over c2 h2. Now, remember all that stuff I was saying about trig? But all we care is about the ratio of the sides? What are these? What's x over h1? What's d minus x over h2? What is this side over this side? What's that ratio?
It's cos theta 2.
Cos theta 2. What's the other one? Be careful because the angle is here. So what's the opposite over hypotenuse? That's total. So, right? Opposite over hypotenuse.
Oh, yeah.
Sine, yeah. Okay, but look what we've discovered, right? T prime is minimum. T is minimum when T prime is equal to 0, but this happens only when sine theta 1 is equal to sine theta 2. Now, look how nice of a relationship this is. Oh, yes, cos theta. It's a very simple relationship that nature has naturally optimized for. So this actually gets a name in physics. This is called Snell's law. Light always finds the fastest path of travel. And because we know it, we can actually work out the precise interaction between theta 1 and theta 2. You don't need to know this for math. It's just very interesting, right? That nature is basically naturally applying calculus.
Can you put us through that for fun?
This was fun. This is beautiful. This is beautiful. This is a natural law, right? This is a law of nature. This occurs naturally. How the hell light manages to pick the optimal theta is beautiful. This is amazing, right? If you think about these things, right? Why should nature have figured out calculus? It's inbuilt to the rules of natural law. Right? I am teaching you the rules of the universe. I am, though. This is how you codify the rules of the reality in which we live. Right? So if you don't find this interesting, I don't know what you do. Right? But look how simple the relationship is between. How can this be so simple? Right? That the light hits and does that, and that's how they're related. And that you know enough mathematics to prove something of natural law. If you don't find that interesting, I can't help you. Right? But it's beautiful. It could be beautiful. That there's this interplay between nature and mathematics. Okay, so what do we got? Okay, so why don't you pick one question from what I gave you and give it a go. Right, you're going to need a lot of practice when it comes to these things, right? Because there is no standard way of changing word problems into problems of math. I'm confident once you get that translation accomplished that you are mathematically competent enough to perform the mechanics. Right? So be sure to practice mostly extracting the problem into one of calculus. Yeah.
This is like out of, it's not related to the just a general math question.